All right, so for most of chemistry history, people desperately wanted to... People who first observed. Thank you. No one's noticed that all day. Who first observed a nuclear transformation? What chemists had been dreaming of for thousands of years. Not LeBron James, Lord Rutherford. Really close. He was another Lord, right? What was it? Remember, he played around with alpha rays. And he played around in atmospheres loaded with nitrogen. What he noticed is that ever so often he would detect the presence of radioactive oxygen. What he theorized was that the nitrogen-14 was becoming a new element, which was really cool because that led us to believe that maybe we could make some other types of atoms. This was the first observed example of a transmutation, when one element becomes another. What was produced by these reactions? Larger atoms. But what was the problem? Think about it. Alpha rays, positive or negative? Positive. Nucleus, positive or negative? Positive. So, Sasquatch, what is the problem with trying to bombard positive particles with positive particles? They will tend to repel each other. So it really can't happen very effectively at our speeds or at their speeds, their natural speeds. So what they had to do was create these things called super colliders or particle accelerators in order to whip them up, moving so fast that when they collided, they would stick together. The problem is that if you're trying to make gold in a particle accelerator, keeping in mind that it probably costs millions of dollars to run the particle accelerator for an hour, what if you collect a few grams of gold? Okay, you've lost a lot of money, considering you could have gotten gold for, a few $100s an ounce. So, no, we can make gold, it's just not very cost efficient. So, what other particles did they start playing around with in order to make them do the same thing? Don't want to use protons because that don't work. How about neutrons? Yeah, what's the advantage of using neutrons? Yes? So will they repel off the nucleus? No. So they started playing with neutrons, slamming them into larger atoms like uranium-238, and it would become uranium-239, which was unstable, and uranium-239 would break down into neptunium. Look at where neptunium is on the periodic table. It's right next to uranium. Could we do it again? Could we hit neptunium with a neutron and make it become plutonium? Yes, we could. And that was the secret of X10. By slamming uranium-238 with neutrons, we were able to make plutonium, which was fissionable. What does it mean to be fissionable? You'll find out tomorrow. So, what has resulted from this type of bombardment? Heavier atoms have been created. Eventually, neptunium, plutonium, americium, many of these things were made right here in Oak Ridge through the 1950s and 60s. Americium, in particular, was created here in Oak Ridge. These are called the transuranium elements. The transuranium elements. So, how do we detect radioactive particles? What instrument is used? A Geiger-Müller counter. Here's one right here.
Is that what keeps beeping?
Yes.
Okay.
If it's irritating you, every time you hear a beep, that means a tiny little atom has exploded near this Geiger
That's
counter.
very irritating.
Oh, it's going to get worse.
It does?
Yes.
Oh, great.
Geiger-Müller, or GM counters, are one of a class of gas-filled radiation detectors that operate by using the ionizing nature of alpha, beta, and gamma
Beta. I
radiation.
love that. Beta.
The GM tube is a sealed metal cylinder containing a low-pressure inert gas, such as argon or neon. A thin metal wire runs down the center of the tube, which is electrically insulated from the outer cylinder at the rear of the tube. The front of the tube is sealed with a radiation window that is specific to the typical radiation to be detected by the counter. For example, a thin mica window is used if the tube is to be sensitive to alpha particles and low energy beta particles, both of which have low penetrating power. A thicker window, or a different material, such as glass or a thin sheet of metal, is used for high energy beta particles, while for gamma rays, the tube is often sealed without a window. The inner wire and the outer cylinder are maintained at a potential difference of about 1 kilovolt, and in the absence of radiation, no current can flow through the inert gas between the central anode and the outer cathode. The connections are made via wires into a connecting housing that fits over the rear of the tube. An outer tube guard will typically screw onto this to protect the actual GM tube. This tube guard can be open at the end or be covered by an end cap energy filter to change the energy and particle sensitivity of the device, or, if a carefully calibrated design is used, allow for ambient dose measurements rather than ambient count measurements to be made. The wires connect the tube to the control electronics, which supply power, perform the counting operations, and provide other functions such as conversion from counts to dose, data logging, data averaging, and driving the display. The tube works on the principle of gas amplification. Incoming radiation ionizes some of the inert detector gas, resulting in a free electron and a positively charged ion. The electric field inside the tube attracts the charged ion to the outer cathode, while the electron is attracted towards the central anode. The charge migration in the tube leads to a reduction in the potential of the anode and an increase in the potential of the cathode, either of which may be detected as a signal by the counter electronics.
Okay, don't completely understand this. I'll share with you what I do. Okay, so here I have this tube, and it's full of argon gas. This is a thin window. I don't even want to touch it with my hands, with my fingers, because I might break it by just touching it with my fingers. Okay, so whenever a particle explodes outside this window and the radioactive particle, alpha, beta, or gamma, were to come by and actually go in there, I mean, imagine there's a lot of these guys that are going to go off in different directions, so we're just lucky that some of them go in there. If we're lucky enough for them to hit an argon gas, the casing is going to be negatively charged. Why? I don't understand. I don't understand electricity much. And this wire is positively charged. So when the argon gas gets hit by the radioactive particle, the electron goes careening off and is attracted to this wire. The argon gas goes up and actually picks up an electron. Since it's lost an electron, it's positive, it picks up an electron and goes back to being just a normal argon again. I don't understand how, but somehow whenever that electron touches the wire, this machine over here can detect it. So every time it beeps, what you're hearing is something exploding near this window, and you're getting a particle in there, or gamma. Okay, so let's try something here. Who do you think might be radioactive in this class? Natalie, come over here, Natalie.
Do you have any bananas?
Okay, so Natalie, stand over here, and face the class. Okay, what we're going to do is we're going to test her on the left side and on the right side to see if she is radioactive. So on the left side, nothing, normal, normal. Then on the right side, keep facing over there. Okay, that was weird. Going down further, up your arm again, towards your head. Okay, let's check again. Do you have an earring?
No.
Do you have an artificial ear?
No.
That is really weird. Let's check again. Okay, let's check your right side.
Not that.
Oh, yes, your left side. Your right side. Okay, go sit down. I have not had that happen all day long. You may want to talk to your parents about this. I haven't had that ever happen. Are you okay? I mean, does it feel hot or anything?
No, but it happens in middle school too when they have a guy through counter.
To you?
They always
And was your
stopped at
teacher
my desk.
holding this?
They had a piece of plate under the desk.
So I'm not the first teacher to freak you out. I was waving this right.
I know.
Oh. How did you know?
Because
It had
the
already
middle school
happened.
teacher did it to me too. It's always me.
Jeez. Well, you volunteered. Usually the ones who volunteer are the most gullible.
Will it stop beeping now that it's in its thing?
Nope.
I hate life and everything in it.
I can explain the concept of half-life, and if given the amount of an isotope and its half-life, I can do some simple calculations. So we're on the back of your homework from Friday, so you might want to get it out.
Just like with other chemical reactions we've talked about, we need to know more about a nuclear reaction than just what's reacting and what's being produced. Probably the most important thing to learn is how much of the product is being made and how fast. Now, you've heard of half-life. It's the measurement that tells us just that. The time it takes for exactly 1/2 of the sample to decay. Different nuclei have different half-lives. By knowing the half-life, we can calculate how much of a sample will be gone in a given amount of time. For example, the half-life of phosphorus-32 is 14.3 days. So if you start with a 100-gram sample, after about 2 weeks, you'll have 50 grams left. After another 2 weeks, half of the remainder would decay, leaving only 25 grams of undecayed phosphorus, and so on. Now, you might be asking, if radioactive elements are always decaying into more and more stable isotopes that are eventually no longer radioactive, why are they still around at all? Fascinating question. You seem to have brought your clever pants today. Well, it's fairly simple. Given enough time, all radioactive elements would decay into non-radioactive forms. Even ultra-stable bismuth with its half-life longer than the age of the universe.
By the way, check out the little cartoon they have for bismuth. What does it look like?
Pepto-Bismol.
A bottle of Pepto-Bismol. Why did they use Pepto-Bismol to indicate bismuth?
Bismol sounds like Bismol.
No, because there's actually bismuth in Pepto-Bismol.
But elements with short half-lives are around because they were decayed into by elements that recently decayed into them. The chain of decay from the element originally produced in whatever supernova created them to the elements that exist on Earth now lasts billions and billions of years. Also, I should note that some radioactive isotopes like carbon-14 in the atmosphere are constantly being renewed by cosmic rays. Now,
Okay, so what is half-life? Half-life is the amount of time that it takes for half of all the Maries to go through all their decay series to become, Tom? What was your end? Matt. To become Matt. Okay? So here are 1,000 Maries. Let's say that her half-life is 5 days. After 5 days, how many Matts do you have? 500. And how many Maries and all her radioactive daughter nuclides do you have? 500. 500. Okay? Now, the most common misconception that people make is that after another 5 days, all of the Maries have become non-radioactive, and they would be wrong. Because half-life means that after a certain amount of time, all you have left is half of the original amount. Okay? So after 5 days, you have 250 radioactive Maries still around. After another, after 15, right, another 5 days, total of 15 days, you have 125. 67 and a half, right?
Yeah.
67 and a half, and then 33 and a quarter, and you could go on and on and on and on until I can't fold this piece of paper anymore. Yes, Max?
So what if you have one atom?
Well, obviously, if you have one atom, then half-life doesn't really work for one atom. Okay? So, what is half-life? The amount of time that it takes for half of a radioactive atom to go through the process of decaying into a non-radioactive atom. Some examples. Here are different flavors of radium. Radium-223 has a 12-day half-life. 224, 3.6 half-life. 225, 15 days. 226, 1,600 years. 228, 6.7 years. Now look at their masses and look at their half-lives. Do you see any patterns? No, there's no pattern there. We don't. There's no way to predict it. We don't understand it. Yes.
If there's no way to predict it, how did we figure out that?
Let me show you.
Six lasts 16
Let me
years?
show you. Okay. Here is a demonstration of half-life that is really neat. This is not something that you would normally find in a high school. You are fortunate in that you live in the atomic city, and we have here one of the most valuable companies for education purposes, for radiation education purposes, in the country, in the world. It's called Spectrum Techniques. These tiny little discs that I use to try to freak out Natalie. These discs can be found in all universities. This is an alpha emitter. I have beta and gamma back there. Guess where these things are made? Pretty much the only place that they're made in the world.
China.
No, just down the road, Union Valley Road, Spectrum Techniques. And because they're so close by and they love us here at the high school, they lend me all sorts of really cool things. Inside this cylinder are tiny little spheres containing cesium-137 with a half-life of 30 years. Now, I don't understand how or why, but as soon as that cesium comes in contact with the air, it will become barium-137 with a half-life of, I'm not going to tell you. You're going to figure it out. Okay? So this liquid right here is called an eluting solution, and I don't understand how it works, but what it does is when you push it through, it removes the cesium-137 and lets it come out the bottom, and we'll be able to capture the now barium-137 and see how radioactive it is. Let me set up. You need to take out a sheet of paper because you're going to record these amounts. You're going to record these amounts, and tonight, as part of your homework, you're going to graph this. I need 7 drops. Count with me. 1, 2, 3, 4, 5,
6,
7. All right, pop this sucker in here. Holy smokes, that very radioactive substance was that close to Natalie. And we're going to let this run for 30 minutes. Oh, one of them did drop on the floor.
Right. Is there a mute button?
No. It's going to annoy you for 30 minutes. Okay, now let me tell you about this. You guys were being annoyed by that constant beeping. What was that beeping coming from? It was coming from the natural radiation that can be found in this room. Okay, it's not just because we're here at Oak Ridge High School. You can find this radiation in your own bedrooms. It's natural. It's there. It's called background radiation. What I did on Friday is take a 10-minute count, making sure all my sources were far away, because I wanted to get a feel for how radioactive the air, this environment is here in LC215. So, here are the numbers. In 10 minutes, they went 23, 29, 31, 24, 19, 25, 38, 27, 36, and 25. for an average of 27.6, I think, which we said was 28. Jot that down. So the normal background radiation is 28 counts per minute. What does that mean? Check this out. The first reading that we took of the barium-137 was 23,485. So write down number 1, 23,485. What do we need to do with the number 28? Think about it. No. Of the 23,458, can we say that all of those radioactive decays came from the barium? No. On the average, 28 of those came from the air around it. So every time you take a reading, and you will take 30 of these readings, you need to subtract 28 from it. Second reading, 19,151, and then subtract 28. Tonight, because you will end up having to graph this beautiful set of data points. Okay? Now it's time for you to whine. If you so wish, you have 2 seconds to whine. Ready? 1, 2. Okay, no more whining. Third point is 14,997. Yes. From every reading that you take. Because 28 from this number right here, 14,997, subtract 28, and that's the number you will use. Why? Because 28 is the background radiation. That is what is naturally here. That is how much we began with. Think of it. Good. Yes?
So is our graph comparing the counts per row?
Yes. The time is going by. We're controlling time. We're going to make it go 30 minutes. We're controlling the time. And what we cannot control is how many decays happen. So what goes on the x-axis? Time. And what goes on the y-axis? Counts per minute. The counts per minute. Here's another one. 11,870. 11,870. All right, we'll come back to that. Thank you. No. Don't know. How long will it take for a sample containing 1 mole of radium-223 to reach a point where it contains only a 1/4 mole of 223? There is an equation for using this, but frankly, in honors chemistry, these questions will always be simple enough to do it this way. Put your starting amount and divide it by 2. A half-life has now gone by. So you record 1 half-life. How much is left after 1 half-life? Is 0.50 moles our goal? No. So let another half-life go by. This is the second half-life. How much do you have left? 0.25. Okay, is that our goal? No. That is our goal. So how many half-lives went by? 2 half-lives. What is the half-life of 223? According to that chart that we saw a few minutes ago, it's 12 days. So how much time will have to expire in order for us to take that sample from 1 mole to 0.25 moles? Half-life was given to you.
So
2 half-lives have gone by. 12 times 2 is 24.
So these questions will we need to research the half-life?
Nope, it'll be given to you. Here is a radium clock. You're going to see what terrible, horrible things happened to the young ladies who made these clocks. Back in the 1920s, I think, these radium girls were all put in this paint shop, and they were given radioactive radium that happens to glow in the dark. They took their little brushes and they started to use the radioactive radium to paint the arms. And I actually have some of the arms, clock arms from these watches that I can let you see, and we can measure their radioactivity. And they would actually paint the numbers that you had glow-in-the-dark watches. So these girls, the brushes would get all frazzled over time, so guess what they would do to them in order to get them to be nice and smooth? They would stick them in their mouth and squeegee it with their mouth in order to... You will see pictures. Terrible, horrible. Okay, radium-228 is 6.7 years according to that chart. We start at 8 times 10 to the negative 7th. We have to go to 1 times 10 to the negative 7th. Since they're both times 10 to the negative 7th, what can we do with times 10 to the negative 7th? So we need to go from 8 to 1. Ready? 8 divided by 2 gives you 4. And that's 1 half-life. 4 divided by 2 gives you, and that's another half-life. 2 divided by 2, and that's another half-life. And the really cool thing is, that was our goal. That was our goal. So, how many half-lives? 3 years. Each half-life takes
6.7.
So how many years ago was that watch made? Around 20 years ago. Okay, let's go back to Marie's original question. How do you find the half-life? Okay, let's look at this. First of all, before we look at it, let's make sure we get all our readings. Did you get 9177? Okay, number 6 is 6988. Number 7 is 5512. Number 8 is 4265. Number 9 is 3254. Okay, let's start with the beginning. Take out your calculators. What would half of 23,458 be?
11,739.
11,700. So where does it...
Between 4 and 5.
So how many minutes pass by? Let's see.
4.
1 minute? No. Be careful because this is our starting point, right? 1 minute? 2 minutes? 3 minutes. 3 minutes. The half-life is a little over 3 minutes.
But if you have a material that's so radioactive, it gives you a gigantic number of counts. Like the one that was 1,600 years, you couldn't possibly do it in one day. Wouldn't that take a number of weeks?
If the half-life is 1,600 years, yeah, I mean, this
It's
would...
a huge number.
If it's 1,600 years, it'd probably be less radioactive than background. So you're right. It's something, a lot of this is math, right? So it's statistics. You're going to study this when you take AP statistics. Actually, I think half-life is something you study in Algebra 2. Maybe?
No.
Where do you study half-life?
I don't know.
No one? Okay. You haven't studied half-life. Whatever math you're in, you haven't studied half-life yet? Maybe it's just in statistics. All right, let's take a few more. Did we do 3254?
Yeah.
2503? 1832? All right, let's take another one. Let's see, we were here, 11,870 divided by 2.
5,935.
So, it's between the second and third minute, which is right, because the actual half-life is 2.55 minutes. So it should be between the second and third minute. Let's do another one, 5512. What is it?
2756.
Okay, so it should be 1, 2, 3. This is it. Between the third and second minute is the half-life. And that's right, it's 2.55. Okay, so here's our starting point. 1, 2, 3. So if it was 3 minutes, it would have been 2503. Because it's 2570 something? What is it, 25?
Where?
What's half of 5512?
2756.
Okay, because it's 2756, then it's somewhere between the second and the third minute. And I can tell you from the label, it's 2.55 seconds. 2.55 minutes. Which is right. Okay? Let's get back and let's do another example. And then let's talk about one of my favorite topics, carbon-14. The watch in the previous picture, we've already done that one. Cobalt 131 nuclide has a half-life of 30 years. Do I have to give you half-life? Yes, I have to give you half-life. And if I don't give you half-life, then what I want you to determine is half-life, and we just did that, right? Just how long it takes for half of it to decompose. After 120 years, about 3 grams remain. What is the original mass? The previous two questions, I was asking you for what is the final mass. Now I'm asking for what is the original mass. In other words, you need to go backwards. Okay, so if you have 120 years expired and your half-life is 30 years, how many half-lives went by? Okay. So we start out with 3 grams. Before we divided by 2, what should we do now? So multiply by 2 equals, that's 1 half-life. Multiply by 2 equals, that's 2 half-lives. Multiply by 2 equals, that's 3 half-lives. Multiply by 2 equals, that's 4th and final half-life. So the answer is 48 grams. Easy peasy lemon squeezy. AP chemistry will be a little harder, but there will be an equation involving natural log that will be given to you that you can apply. Okay? So the stuff that I give you is stuff that you can probably do in your head, but I still want you to work it out. You need to be in the habit of always working things out. The stuff that AP chemistry you'll have to deal with, you'll have to use an equation for. What is the most practical use for half-life? Anybody know? Yes?
Carbon dating.
Yes! Carbon-14 dating. The dating of archaeological remains. And the most accurate way of doing so is through carbon-14 dating. W.F. Libby came up with this in the 1940s. It's based on this equation. In the upper atmosphere, normal, natural, non-radioactive nitrogen, if it encounters a neutron from space, are we being showered with neutrons from space? Yes, all the time. Are those neutrons dangerous? Yes, they are. Why are we not dying from these neutrons? because our friend nitrogen-14 intercepts him high up in the atmosphere. Unfortunately, it costs our friend something, and that is that it is converted into radioactive carbon. That carbon-14 finds its way into the carbon cycle, becomes carbon dioxide. Plants take it up. We eat the plants, or we eat the animals that eat the plants, and now it's in Noah. Carbon-14 is in Noah. Radioactive carbon-14 is in Noah. And Noah can say, without any equivocation, that he is radioactive. Radioactive. He's radioactive. He's radioactive. Now, what happens if he excretes? If he does number 2 or number 1? What happens to the carbon-14? It goes out. And what happens when he eats? Comes back in. So through his lifetime, he is going to have a steady amount of carbon-14 in his body. Don't eat. Just don't eat, just excrete. Now, the carbon-14 in time inside his body, out in the atmosphere, perhaps some of this beeping is coming from carbon-14 blowing up. Carbon-14 decays by beta decay to become nitrogen-14, and the cycle continues again. That's happening. It's happening right now in his body. So we would get a reading. It's rare. Nope. You got it on you as well. Marielle, you are radioactive. Radioactive. Yes. Yes. But it's measurable. And the key thing is, when Noah dies, will he... Sorry, but we're all going to die. I hate to tell you this. I hate to be a bearer of bad news, but you're going to die. Everyone here dies. Everyone in this room is going to die.
Can I die
Sorry.
first?
Sure, you can die first. Okay, Noah. What happens when you die? Will you eat any more? No. Will you, guys, will you excrete any more? No. So the amount of carbon-14 you had when you died will stay there. But what happens over time? It will decay. So consider him to be very radioactive upon the point of death. The older his body lays there, the longer his body lays there, the less radioactive he will become. The half-life for carbon-14 is 5,730 years, I think. Yeah, 5,730 years. Sorry, I think I have it in another... Yeah, 5,730 years. So, if his body lays there for 5,730 years, and we were to measure his radioactivity, he would be half as radioactive as a living creature. What does that mean? That means anything that was alive at some point, we can burn, convert to carbon dioxide, measure how radioactive that carbon dioxide is, and compare that to how radioactive living material is, and then just do some simple calculations. So, 10,000 years from now, we can dig up his body, take a small sample, burn it, and figure out within about 50 years, not when he lived, but when he died. When he died. Yes?
If that's such a thing that if you want to find out how old it is, you need to burn it, wouldn't that run into issues with if you have like extremely rare fossils, you have to burn it?
Wait, first of all, it doesn't work with fossils because fossils have been fossilized. They have been converted to rock. Okay, so it needs to be previously living material. For example, here it is, the Shroud of Turin. Have you heard of the Shroud of Turin? This is a negative of the supposed burial cloth of Christ. Okay? I'll show you a video of this. This is the most scientifically tested historical artifact in the history of mankind. Do you see the image? Here is hair.
What?
Here is the face,
Got a face.
mustache, beard, eyes. Here is arms, hands, legs. Now, it is very hard to see this in the actual image. Back in the late 1800s, early 1900s, this photographer by the name of Secundo Pia was the first one to take a picture of it, and as he was developing the film, he realized that the image in the negative was more realistic than the actual image. The Catholic Church, back in I think it was 79, allowed a group of scientists to come and test this shroud. They would not allow them to cut a piece of the shroud off. So all they could do was take tape and press it onto the linen and pull off fibers. And they were able to collect enough fibers to run at least, I think it was a couple of carbon-14 tests. And it came that it was around 800 years old. So, fraud, 1200s, Renaissance. Okay? But, here's the problem. Why can we conduct this test on this shroud? What is it about this shroud that is testable? What's it made of? No, it's made of linen. And what is linen made of? Cotton. Cotton. Was cotton alive at one point? Yes. Okay, so the fibers themselves should be testable. But here's the problem. Only in the last 30 years have they placed this shroud in an argon-rich atmosphere and pumped all the air out of it. So for at least 800 years, this shroud has been in contact with the open air. What's in the air? Pollen, yeast, fungus, bacteria, viruses. They would take this sucker out and let people touch them, kiss them. So every time it was touched, every time it was kissed, what was left behind? Younger organic material, younger living material. So, yes.
So, do you think if they actually took the actual cloth and then burned it, they would get more information?
Yeah, and here's the deal. Now they've gone back. I mean, even at that time, they were skeptical of the 1200 date because they had such small amounts of material. They did not have the ability to clean it of any foreign materials that might have been on top of the fibers, because they knew they would have lost too many fibers and not enough. So they've come back to the Catholic Church and they said, you know, sorry about the 1200 date. I know that you're really disappointed, but if you were to let us cut a whole piece of it off, postage stamp size pieces, then we're confident we can get rid of any contamination on it and get a truer reading. And the Catholic Church has said, no. Or in Italian, no.
Why would it matter if it's not even the Shroud of Turin? The readings are wrong.
Okay, in a way, that's the way they think about it. What does it really matter? It is a matter of faith. And you're going to... Now, this is not the only thing strange about this shroud. This shroud, this image is very bizarre. I'll let the video take care of that for you. If you are interested and want to read more, you can get the latest on www.shroud.com. What's the second most popular, most famous carbon-14 artifact? Does anyone know? The Iceman. that they found in the Alps. Yeah, the one that was shriveled.
watched the movie in
Miss Webb's
That's right.
Yes, we did.
How about this Viking ship that was discovered in the ice? Can it be testable?
Yes,
Why?
because it's wood. Wood
Because
survived.
wood at one time was alive. What about this mummy? Can it be testable?
Because it's a mummy.
He's not a mummy. He's probably a daddy. Okay, but the mummy, he's working on the mummy. All right, there's probably still some stuff that's not bone, right? Some stuff, some muscle fibers that can be removed and tested.